Exponents. On July 4th, 1997, the Mars Pathfinder lander touched down on Mars. It had traveled 4.013 times 10 to the 8th kilometers from Earth. 2 days later, the Pathfinder's Sojourner rover was released and transmitted data from Mars until September 27, 1997. The distance Pathfinder traveled is written in scientific notation. A number is in scientific notation when it's in the form a times 10 to the n, where a is a number between 1 and 10, and n is an integer. At their closest points, Mars and Earth are approximately 7.5 times 10 to the 7th kilometers apart. Write this distance in standard form. So 7.5 times 10 to the 7th, we multiply by 10 to the 7th, which is going to mean moving the decimal 7 places to the right. So 1, 2, 3, 4, 5, 6, 7, and we fill all of those spaces in with zeros. So that ends up being 75 million kilometers. 75 million. How many times farther is the distance Mars Pathfinder traveled than the minimum distance between Earth and Mars? So the Pathfinder, if we recall, was 4.013 times 10 to the 8th. 4.013 times 10 to the 8th, and we're going to divide that by 7.5 times 10 to the 7th. So we have 10 to the 7th here. We can cancel out 7 of these 10s. And so that ends up being 40.13 over 7.5, which we can do on our calculator. And that ends up being about 5.35 times as far. So Mars Pathfinder traveled 5.35 times the minimum distance between Earth and Mars. Some calculator hints. Say that we want to do 100 divided by 6.67 times 10 to the negative 11th. If you just put that into your calculator in that order with no parentheses, your calculator is going to do order of operations. So your calculator is going to do 100 divided by 6.67 and then multiply by 10 to the negative 11th. And that's why you would get a power. This is 1.5 times 10 to the negative 10th. But if you have this very small number in your denominator, you should end up with a bigger number. And so what you need to do to ensure that all of this is in the denominator is you need parentheses around that denominator. And so when you do that, you get the same thing, but you get a power of times 10 to the 12th, which is the correct answer. Or, if you want to save yourself a few keystrokes, you can use the E button. That is this E that's right above your comma. And so that is the equivalent of the times 10 to whatever this power is. But your calculator knows that all of this goes together when you use the E button. And so you don't need parentheses if you do it that way. And this also gives you the correct power of times 10 to the 12th. So properties of exponents. Suppose m and n are positive integers and a and b are real numbers. The following properties hold. You have the product property. When you multiply two exponents with the same base, you are going to add their powers. So 16 to the 3rd times 16 to the 7th. You add 3 plus 7 and you get 16 to the 10th. Similarly, for the quotient property, you divide two bases with two exponents with the same base. You're going to subtract the powers. So 15 to the 6th over 15 squared. You're going to subtract and get 15 to the fourth. When you raise a power to another power, you multiply them. 9 to the third squared is going to be 9 to the sixth. If you have things that are multiplied or divided inside your parentheses, you can distribute that power. So 5x to the third is 5 to the third x to the third. Same thing for division. 3 fourths to the fifth is 3 to the fifth, 4 over 4 to the fifth. This only works for multiplication and division. It does not work for addition and subtraction. X plus y squared does not equal x squared plus y squared. Do not do that. Anything to the 0 power is equal to 1. And a negative exponent is the reciprocal function. So b to the negative n is 1 over b to the n. So 7 to the negative third is 1 over 7 to the positive third. And that also, for fractions, you flip them. So 3 fourths to the negative fifth is going to be 4 thirds to the positive fifth. And you flip the fraction. Evaluate each expression. 2 to the fourth times 2 to the eighth over 2 to the fifth. We're multiplying two exponents with the same base here, so we're going to add these powers and make that 2 to the 12th over 2 to the fifth. Now we're dividing two exponents with the same base. We're going to subtract those powers, and that's 2 to the 7th. And 2 to the 7th is 128. 2 fifths to the negative 1. That's the reciprocal. We're going to flip that, and that's 5 halves just to the first power, which is just 5 halves. S squared t to the third to the fifth. We're going to distribute this power, this fifth power here that's outside the parentheses. And so s squared to the fifth is s to the 10th. We multiply those powers. And t to the third to the fifth is t to the 15th. X to the third y over x to the fourth to the third. This is going to be x. We'll leave this x to the third y for right now. X to the fourth to the third, we multiply those and get x to the 12th. Now we have x to the third over x to the 12th, and that's going to end up getting us x to the 9th in the denominator. We can think of this as x to the 3 minus 12, which is x to the negative 9th, and the negative means it goes in the denominator. There's no other y's in there to combine with, so that y is just going to stay in the numerator. Expressions with rational exponents can be defined so that the properties of integral exponents are still valid. Consider the expressions 3 to the 1/2 and 12 to the 1/3. Extending the properties of integral exponents gives us the following equations. Right? So 3 to the 1/2 times 3 to the 1/2, we would add those powers and get 3 to the 1, which is just 3. So what is something that when we multiply it by itself, we get 3? That is the square root of 3. So 3 to the 1/2 is equal to the square root of 3. We can do the same thing with 1/3. 12 to the 1/3, when we multiply that by itself 3 times, we would add up those 1/3 and get 1. So what's something that when we multiply it by itself 3 times, we get 12? That would be the cube root of 12. So a 1/3 power is a cube root, and so on for all fractional exponents. For any real number, b greater than or equal to 0, any integer n greater than 1, b to the 1 over n power is the nth root of b. Also works if b is negative and n is odd. You can take odd roots of a negative. So 125 to the 1/3 power is going to be the cube root of 125. And 125 is 5 times 5 times 5, so the cube root of that is just 5. The square root of 14 times 7, because these are just exponents, we can use our exponent rules. Namely, we can make this the square root of 14 times 7, which is 98. But more specifically, we can make this 2 times 7 times 7. We got a pair of 7s in here, so we can pull that out, right? We could make this the square root of 49 times the square root of 2. And square root of 49 is 7, and then that 2 doesn't have a match, and so that's going to stay in there. It's going to be 7 square root 2. We want to distribute this 1/4 out front. This is going to be 81 to the 1/4, and c to the 4 times 1/4 is just 1. The square root of 81 is 9, so the 4th root of 81 is equal to the square root of 9, which is 3. So 3c is our correct answer here. This we can do 9 to, well, let's do it just to write out all of our steps here. 9x to the 3rd to the 1/6 power, which would be 9 to the 1/6 power x to the 3/6 power, or x to the 1/2. This 9 we could write as 3 squared to the 1/6, x to the 3/6, which would be 3 to the 1/3 power, x to the 1/2 power, which is perfectly fine way to do it, or you could do it as the cube root of 3 times the square root of x. Either one would work. For any non-zero number b, any integers m and n, where n is greater than 1, and m and n have no common factors, b to the m over n is equal to the nth root of b to the m, or the nth root of b to the m, except where the nth root of b is not a real number. So 625 to the 3/4, I tend to prefer to doing it this way, because taking the nth root is easier when your number is smaller. If you raise it to the m, then you got to take the nth root of a bigger number. So I would do this as 625, and this is going to be the 4th root of 625, and then raise that to the 3rd power. So the 4th root of 625 is 5. 5, 25, 125, 625. So the 4th root of 625 is 5. So 5 to the 3rd is 125. You could also do it as the 4th root of 625 to the 3rd, which is the 4th root of what number is that? 244,140,625, but you probably can't do that 4th root in your head. Still ends up being 125 though. For this one, let's go ahead and use our division rule. We're going to do 16 to the 3/4 minus 1/4, which is 2/4, which is 16 to the 1/2, which is the square root of 16, which is 4. We can switch back and forth between rational exponents and radicals. So in this case, remember that radical is a 1/3 power. So s to the 9th, t to the 15th, all of this to the 1/3 power. going to be 64 to the 1/3 s to the 9 over 3, and t to the 15 over 3. And so the cube root of 64 is 4, s to the 3rd, and t to the 5th. We can also use radicals here to express these. If I want to put all of these in one radical, I'm going to need to get my common denominator for these fractions. Common denominator here is going to be 6. So I'm going to multiply this by 2 over 2, and I'm going to multiply this by 3 over 3, and make this 12x to the 4/6 y to the 3/6. And then I can take the 6th root of x to the 4th and y to the 3rd. And that's putting them all under one radical. To simplify this, again, so for an nth root, I can take things out in groups of n. So for a square root, I can take things out in groups of 2. Here, I have 7 r's. That's 3 pairs of r's, and 1 r left over. Here, I have 25 s's. That's going to be 12 pairs of s's and 1 left over. And here I have 3 t's. That's going to be 1 pair of t's and 1 left over. So I could do it like this. Or I could put them in terms of rational exponents and make this r to the 7/2 s to the 25/2 t to the 3/2. And you can simplify that so you can see 7/2 is equal to 3 1/2. 25/2 is equal to 12 1/2. 3/2 is equal to 1 1/2. So this is that. And then the 1/2, all of these 1/2 are what goes under the square root. If we want to solve 734 equals x to the 3/4 plus 5, first thing that we're going to do is subtract 5. So that's going to be 729 equals x to the 3/4. I'm going to go ahead and put this in, well, actually, no, I don't need to do that. What I can do is, so I'm going to say this is equal to x to the 3/4. Now, if I want to get x by itself, I need to raise this to the reciprocal power. And so when I raise this to the reciprocal power, this is x to the 3/4 times 4/3, and the 3's cancel out and the 4's cancel out, and that's just equal to 1. But I need to do the same thing on this side. I need to raise this to the 3/4 power as well. So if I do 729 to the 3/4 power, that's going to be, ends up being 140.3. Oh, sorry, not to the 3/4, to the 4/3 power. To the 4/3 power, not the 3/4 power. 4/3 power, I knew that should be, is 6,561. So this should be to the 4/3 power, because we raise this to the 4/3 power. And if you do that to the 4/3 power, it's 6,561. Exponents don't need to be rational numbers. Any real number can be an exponent. You will not be able to do those in your head. You will need to use a calculator for that, but that's why we have calculators. So if you want to do 3 to the pi power, you absolutely can in your calculator. If x is an irrational number and b is greater than 0, then b to the x is the real number between b to the x1 and b to the x2 for all possible choices of rational numbers x1 and x2, such that x is between x1 and x2. What that means, for instance, right, if I have, so say 2 to the pi power, pi is between 3 and 4. Right, pi is between 3 and 4. So 2 to the pi is between 2 to the third and 2 to the fourth. So 2 to the third is 8, and 2 to the fourth is 16, and 2 to the pi is 8.8. So obviously closer to the 3 than the 4, closer to the 8 than the 16. And that's it for 11.1. Stay tuned for 11.2, which is exponential functions.